Welcome to today's Explainer, where we're going to unpack a pretty massive breakthrough in material science. If you're an industrial engineer, a facility manager, or honestly anyone dealing with heavy-duty cooling systems, you know the headache of keeping these things running efficiently. Today, we're digging into a technical datasheet for a product called Nfm Ac Condenser, and it proposes a fascinating solution to a problem that's been plaguing the HVAC and heavy machinery world for decades. Let's get right into it.
So how do you protect a system without suffocating it? That's the central paradox here. It's a classic engineering dilemma. These units, whether we're talking about coastal air conditioners or massive industrial radiators, absolutely require heavy-duty protection from some seriously harsh corrosive environments. But here's the catch. Most protective layers end up trapping heat inside. It's exactly like throwing a thick winter sweater on a runner in the middle of a summer marathon. You want to protect the system, sure, but you're actually forcing it to work so much harder.
Here's our roadmap for today. We'll quickly hit the heat exchange paradox, introduce the Nfm Ac nano coating, look at its key technological advantages, dive into the hard technical specs, explore some extreme industrial applications, and finish up with the three-step application process.
Part 1. The heat exchange paradox. First, we really need to look closely at the fundamental problem we're trying to solve.
Think about traditional protective coatings, your standard thick polymeric or epoxy barriers. Yes, they provide a physical shield against corrosion, but because they're so thick, they act as insulators. They block heat transfer, they tank your cooling capacity, and they drive your electricity bills right through the roof. Now contrast that with the Nfm Ac coating. It takes a completely different microscale approach. This stuff sits at just 6 to 8 microns thick. It's what they call thermally transparent. So instead of blocking the heat, it lets the system breathe and run efficiently, which translates to some serious cumulative energy savings over time.
Section 2. Enter Nfm Ac nanocoating. Let's look at how this alternative actually works on a chemical level to solve that paradox.
This coating, developed by Nano Z Coating, is definitely not your average hardware store spray paint. It's a highly specialized, solvent-based formula. The technical sheet calls it a modified hybrid nanomatrix. Basically, that means it uses a silica-based inorganic network mixed with organic flexibility. And the coolest part, it creates actual covalent bonds with non-ferrous metals, like your copper and aluminum, so it doesn't just sit on top of the surface like a shell, it chemically links up with the metal itself.
Which brings us to the crucial concept of thermal transparency. This is literally the superpower of this coating, because its physical footprint is so incredibly small. Again, we're talking just 6 to 8 microns. It doesn't act as an insulating barrier at all. The source text is very clear that this preserves 100% of the original heat conductivity. The unit stays perfectly protected, but you don't lose an ounce of cooling efficiency. It's all the armor with none of the weight.
Section 3. Key technological advantages. Beyond just letting the metal breathe, this chemistry packs some pretty aggressive defensive features.
Because of that covalent bonding we just talked about, this coating isn't going to peel or crack, even when the machinery is vibrating like crazy or going through massive temperature swings. On top of that, it's actively hydrophobic and oleophobic. It repels both water and oil. That essentially creates a self-cleaning mechanism where dirt, soot, and mineral deposits literally just wash away when it rains. Add in 5 to 10 years of absolute UV stability, and it even keeps the painted elements from fading or crumbling in the sun.
Now, if you're dealing with a highly corrosive industrial environment, they make a premium version of this coating, and it is tough. It can withstand extreme chemical exposure across the entire pH scale, from 1 all the way up to 14. So whether it's getting hit with harsh acidic fumes or incredibly powerful alkaline cleaners, it just holds up.
Section 4. Technical specifications. All right, let's pull back the curtain and look at the actual numbers.
One of the absolute standouts here is the dynamic viscosity. It sits at a remarkably low 1 to 10 millipascal seconds. For context, that means it flows almost exactly like water. That ultra-low viscosity allows the liquid to seep incredibly deep into densely packed radiator coils, intricate solders, and those super tight galvanic connections. It makes sure every single micron is covered before it cures into that 6 to 8 micron dry film. Oh, and a single liter? That gets you an impressive 50 to 80 square meters of coverage.
Take a second and look at this number, greater than 2,000. That is the number of hours this coating survived in an extreme salt spray test, which, if you're in the industry, we know is a massive benchmark for reliability.
Passing those highly specific international corrosion standards, DIN 50021 and ASTM B117, proves this isn't just theoretical lab protection. Surviving over 2,000 hours in a concentrated salt fog chamber means this stuff is built for the absolute most brutal salt-heavy coastal environments on the planet.
Section 5. Industrial and Extreme Applications. So with specs like that, where is this high-grade chemistry actually being deployed in the real world?
The use cases are wildly diverse, but they all share one core trait: extreme conditions. We're talking coastal air conditioners constantly taking hits from sea salt spray. That's the extreme C5 or CX corrosion classification. We're talking massive radiators on heavy mining trucks absolutely caked in soot and mud. But crucially, by sealing the microscopic meeting points between copper and aluminum, this nanoshield completely prevents galvanic corrosion. That is huge because galvanic corrosion is literally the #1 cause of gas leaks in air conditioning systems.
Section 6. The three-step application process. Despite how advanced the chemistry is, putting it on is actually pretty straightforward.
The technical sheet breaks it down into 3 fairly simple steps. Step 1 is a heavy wash with a water-based cleaner to clear off the surface grime, followed by drying it completely with air pressure. Step 2 is a micro-cleaning phase using a rapid evaporating agent called Component A. This basically nukes any hidden microscopic contaminants to prep the metal. Finally, Step 3 is the actual application. You just use a fine airless nozzle from about 10 to 15 centimeters away to get a perfectly even penetrating mist.
But, quick reality check, you can't just spray it and immediately leave it out in the rain. The safety sheet is very clear that this is a flammable solvent-based product. You've got to use proper ventilation and full PPE, like respirator masks and goggles. And importantly, the system needs a full 70-hour cure time before you can test out its water-repelling magic. You have to let that nanomatrix fully crystallize and bond with the metal.
And of course, formulating a product that demands this level of exact chemical precision requires serious quality control. The manufacturer operates strictly under ISO 9001 quality management systems, so every batch meets those high international standards.
Ultimately, the absolute biggest takeaway from our source text today is this right here. Heavy-duty protection no longer has to come at the agonizing cost of reduced thermal efficiency. By shifting to a nanoscale approach, engineers can protect multi-million-dollar assets from severe corrosion while simultaneously saving thousands of dollars in cumulative energy and maintenance costs. It kind of just rewrites the old rules of heat exchanger maintenance.
So as we wrap up this explainer, I'll leave you with this to chew on. If you're managing facilities or industrial equipment and you're still relying on older, thicker protective coatings, how much extra energy are you burning every single day just trying to push heat through a plastic sweater? It might be time to look a little closer, down at the microscopic level. Thanks for hanging out with me today, and keep asking the right questions.